Morning, guys. So over the last two lessons here, we've been introducing to you two types of graph. One was a position time graph, which basically plots a person's whereabouts over the course of the time interval. That graph there can go into the above region, which is in front of the line, the below region here, which is below the line. It can have curves because we can be speeding up or slowing down. We did yesterday here with the velocity time graph here. If I didn't quite care about where he is anymore, I just wanted to care about at every time interval, is he traveling above the graph here, positive velocities? It means he's going forwards. Is he going backwards? Is his speed actually changing? We had been under the simplification that acceleration is constant, and we basically just dealt with straight lines on a velocity time graph. So what I'm going to do here is I'm just going to give you a quick practice question, making sure we're okay interpreting position time and velocity time individually. And then towards the end, what we're going to do is we're going to see how we're going to switch from one graph over into the other graph. Right? So just for a quick practice here, first example, I'm going to give you a position time graph or a displacement time graph. Right? His displacement is his basically his distance, his how far away he is from the starting line at any given time. Let me give you a few sort of marks here. So we have position time. Let's go up, let's say 4 and 8, -4, -8. So we have displacement here and time. And let's go through, let's say this is actually just 1 second of time. Remember, just for a graph here, you have to be evenly scaled. You can't just suddenly change your scale. But as long as it's constant throughout, we're okay. Let's say we start off here. Let's say our first second, we do this. In the next second, let's do this. In the next second here, let's find that 3, 8 point. So let's go all the way up to there. And then let's do this. Okay. So there's 4 segments here. Of course, I can label it A, B, C, D. Leave this for you to just practice here. Can you identify for me something about his direction, something about his heading, and give me some comments about his speed? Like, is it constant? Is it speeding up, slowing down? This one I gave you the time interval, so I'll probably say between 0 and 1 second, between 1 and 2. I may not even ask you for every single interval, but just for practice, let's do this here. So 2 to 3 seconds, 3 to 4 seconds. I would encourage you to pause the video, try it out for yourself. Remember, just some pointers for yourself. As long as the curve is below, it doesn't necessarily mean you're heading backwards. This just means we're actually behind. Your position, your location is actually before where the starting line is. If your graph ends up going to the positive, it means in front. Similarly, just because you're in front doesn't mean you have to be necessarily continuing forwards. You can actually head backwards, you can be slowing down, you can be doing all that. So let's just try it out here. At the beginning, at 0 seconds, I'm standing at -4. So the picture is like, here's the flag. That was 0 meters. I just happened to be standing at -4 meters. I already was there when I start the clock, right? So I'm at -4. A little bit later, I'm still -4. A little bit later, I'm still -4. That -4 itself is not changing. So in that case there, I can say, well, we're at rest, and therefore we have a constant velocity, which is 0. Remember, constant just means stays the same. This time we actually stay the same at 0 because we actually don't move. Now what we have between 1 and 2, notice that this graph here is going to steadily get closer and closer to the flag. I'm going to be -3, -2, -1. I'm going to actually have to walk forwards. Whenever this graph here is actually sort of climbing and actually going upwards, we actually know that the velocity is actually positive. We're going forwards. How do you tell velocity on a position time graph? Well, it's given by the slant. The slant here is really, really positive at the beginning, and you notice the slant here steadily gets more and more shallow as I step from 1 to 2 seconds. The slant is positive. I know it's forwards, but I know I'm actually slowing down. Again, usually the temptation is, oh, I'm going forwards, I have to be speeding up. Well, no. Direction is something different from acceleration, which is your speeding up and slowing down part. So it's forwards, and it happens to be slowing down. How about between 2 and 3? Between 2 and 3, my slant is also positive, right? I'm heading, now I have hit the starting line here, I've gotten back to the flag, and now I'm starting to walk into the positive distances. I'm actually walking in front of the flag. By the time of 3 seconds, I'm actually at 8 meters, right? Well, I had to have walk forwards, I had to have a positive slope to actually get up to that. This is forwards, so we have a positive velocity. This time, again, the slope happens to be constant. You can even calculate that slope if you want. So the slope here is my distance, my rise is 8. My run is only a 1. 8 divided by 1. I actually have a constant in this case here, constant velocity, and the constant velocity is 8. So at the beginning it was 8, a little bit later it's 8, a little bit later it's 8. The slant itself isn't changing. So that's your constant velocity. And then between 3 and 4 here, we're actually heading backwards. I'm still in front of the line, but I'm actually heading in the negative direction. So we have negative velocities. And in this case here, if you can either use the staircase analogy or the slant analogy here. Using the staircase analogy here, you see that in the same time interval, we actually start traveling longer and longer distances. If I can cover more ground in the same time interval, this part here means actually speed up. For me to have a negative velocity and also speed up, it does mean that your acceleration has to be negative, and that's exactly what it is. So the velocity is constantly getting more and more and more negative, so that implies to you acceleration is negative. I mentioned to you, you can calculate two other things here. I can say, so sort of part B of the question, calculate the average velocity between, let's go 0 and 4 seconds for the entire time interval. So again, realistically, there were all these little complexities. I stood still for a while, then I started moving forwards, and later on I started moving backwards. My speed was changing at some point. Average velocity ignores all of that. Average velocity is back to my blindfold analogy here. At 0 seconds, I see that you are standing at -4. I'm totally blindfolded for 4 seconds. When I take off my blindfold, you happen to be standing here. If I can sort of average out some of those, you went forwards, you went backwards. If I just want to end up at back of the flag, 0 meters, and it took you 4 seconds to do it, I'm actually going to draw that secant line, sort of like a connect the dot line. Basically, I never traveled the speed, but this would be the speed that on average I would need to have over the entire 4 seconds to make sense that when I take off my blindfold, you happen to be back at the starting line. So I drew in the secant line here. The rise in this case here is a 4. It also took me 4 seconds, right? So if I calculate the slope of that there, so this is the slope. I'm going to say slope of the secant line. It's going to be 4 divided by 4. It's like on average, I actually went 1 meter per second. Well, in reality, I was going at 0 for a while. I was going at 8 for a while. I was probably not at 1 for very long. But if I traveled at 1 meter per second for that same 4-second time interval, I can explain the fact that you've covered 4 meters worth of displacement. You actually walk way farther than that 4. But because you sort of double back on yourself, you change direction, we actually don't quite need to get as far anymore. I only need to get 4 meters in 4 seconds, and therefore that's that slope. Especially when we have a curve here, they might be asking you sort of part C of the question here. I want you to calculate or find the instantaneous velocity. Can you calculate the speed at one particular instant in time? Calculate the instantaneous velocity at, let's do 3.5 seconds. And usually, if they're mean, they would usually just mark off a particular segment in the curve. So 3.5 here is right here. Again, the problem is I want the slope because slope is velocity, but I can't find the slope of a single point. So what I'm going to do is using a ruler, you can draw a straight line fit. That straight line fit is called the tangent. Again, the hope of doing the tangent here is that hopefully when I zoom in really, really close on this point here, my tangent basically follows the curvature. It follows sort of the bend of the curve. Now you can take any 2 points that are easy to read. So let me see if I can read that point here. This point here we said the time is 3.5. And then let's see if we can do the y-axis here. Let me match it up here. Maybe we're at about 6. Who knows? And maybe by the time this intersects here, oh yeah, that looks about 5, sure. Right? You'd actually have your graph. So 5, 0. Choose any 2 points on the tangent because that tangent doesn't change its slant anymore. And then do a y2 minus y1, x2 minus x1. I'll do that for you down here. So what we're finding here is actually the slope of the tangent. It's slope in both cases, but we needed the tangent to get our second point. Again, slope is calculated y2 minus y1, x2 minus x1. Let's say this 5, 0 is my point 2, so I'm going to go 0 minus 6 for my point 1, 5 minus 3.5, and that gives me -6, so 1.5. So that gives me my slope of tangent is -4. So at that immediate moment, my slant happens to be -4. A little bit before that, my slant was less than -4, -3, -2, something less. A little bit after that, it's actually going -5, -6, right? But at that particular instant, I'm approximating it should have roughly been about -4. Right? So that's a position time graph here. Let's try out a velocity time graph for practice as well. I generally find people make more mistakes with velocity time graphs, probably because it's a newer graph. So let's just mark off some of these numbers here. All right, so let's just draw a few graphs. Let's go, this one goes straight across, this one goes upwards, and mark off where the 20 would have been as well. And then it comes down. No curves on this graph here, and then maybe this one here just jumps down, just this. Okay. So again, first question is, can you make an interpretation? What is this thing doing at each of these time frames? So tell me something about the direction. Tell me something about his heading. Is he going forwards, backwards? Tell me something about his speed. Is it changing? And then we can sort of allude to acceleration as well. Right? Use a simplification here. As long as we are above, positive velocity means forwards. So I'm above the graph in 3 segments here. I know right away. Forwards, forwards, forwards. For the first 3 segments, positive velocity. Sure, let's label it A, B, C. So for A, B, and C, we're going forwards. The only time we actually drop into the negatives is for part D. Part D, the curve is down here. So part D, we actually are backwards. So negative velocity. How about the speed? So in part A, at 0 seconds, I'm at 10. A little bit later, I'm still 10. A little bit later, I'm still 10. That 10 here is unchanging. In the first segment here, I have a constant velocity of 10. It's constant because it's not changing, so therefore your acceleration is 0. Acceleration is given by the slant, by the slope, while the slope is actually 0. Perfect. Then what? Then in part B, your slant actually switches over to become positive. At 5 seconds, it's slanted upwards. A little bit later, still slanted upwards. A little bit later, still slanted upwards. Your acceleration is also positive. If your velocity and your acceleration are positive, that means you're speeding up. I could have seen that here from the y-axis. I go from a speed of 10, a little bit later I'm 12, a little bit later I'm 14, 16, 18. My speed is actually increasing, so therefore I'm actually speeding up, or you can say accelerating. Part C here usually gives people trouble. People normally, well, it's I'm going forwards, right? That must mean I'm speeding up. Well, no, in this case here, you'll notice the number is actually decreasing. At 10 seconds, I was 20, now I'm 15, now I'm 10, now I'm 5. My magnitude is actually getting smaller. We know it means slow down. We could have interpreted that as well using acceleration. The slant has now switched over into the negatives. It's swapped to slant the other way. If I'm trying to head forwards, I'm trying to go in one direction, but the acceleration is going against me, it's negative. That has to imply I'm slowing down. I still get some positive distance. I still get forwards. It still takes me a little while to actually come to a stop, but definitely I'm slowing down. And then when we switch down to the bottom part here, we're going backwards because the velocity is negative here. The slant has once again become 0, so we expect a constant velocity. Now your constant velocity is negative 10 meters per second. Again, the questions I can ask you in this segment here, we already knew acceleration was a slope, so I can ask you, let's say part B of the question, calculate the acceleration at 12 seconds, right? So I already had decided it was negative. So pick any 2 points that are easy. Well, 12 seconds here is about here. Pick any 2 points that are easy. Well, I have this point here, 10 and 20. This point here, 15 and 0. Those are easy points to read. Acceleration is the slope. So we're going to go y2 minus y1, 0 minus 20. x2 is 15 minus 10. That gives you here negative 20 divided by 5. So negative 4 meters per second squared. It's a little bit hard to read sig figs on a graph, so usually just use that simplification. Just keep everything 2 or 3 sig figs and we're fine. One last question here. Let's calculate the displacement. So I don't know where he's actually starting from, but over these 20 seconds, I want to know sort of how far he gets. Calculate the displacement, I'm just going to say between 0 and 10 seconds. I could have said 0 and 20. I could have done the whole thing. All you need to track here is displacement is given by the area. So what they want is the area under here and the area under here because that's between 0 and 10. And in this case, what we're going to need to do is find, well, 0 and 10 here, or 0 and 5. This is a box, so just length times width. The displacement is given by the area. The first part, let me change color here. The first part is just a box, so a length of 5, a height of 10, 5 times 10. So I get 50 meters for covering that distance. That's going to become important later on as well. Towards the end of yesterday's class, I said, just because we're straight lines doesn't mean we're always just boxes. We sometimes get a trapezoid. Well, let's just separate the trapezoid. What's this bottom box going to be? This bottom box is also going to be a length of 5, a height of 10. That box is there is 50. We now separate our our trapezoid into a box and a triangle. This box here has a width of 5 and also a height here of 10, half base times height. So mathematically I'm doing something like, well, the bottom part is going to be just the 5 times 10. The top part is half 5 times 10 because that's the triangle on top. And in total, that gives you my area for the trapezoid. This part here is 50. This first part of the box gave me 50. That triangle part gave me an extra 25. If you add up all those, I would have covered 125 meters worth of distance. So that is how you figure out what is the displacement over any time interval here. Okay, so I just pulled out the simulation here. I just want to roughly just introduce to you, definitely both of these graphs here talk about the person's motion. Both of them give us information in slightly different ways. It might be advantageous for us if we can somehow, if we have a position time graph, would you be able to draw a velocity time graph and vice versa. So what I'm going to do for you here, I pulled out, so we have a position time graph. This plots his whereabouts. You notice again, the advantage of them is they actually line up the times. When it's 2 seconds on a position time graph, it'll still be 2 seconds on a velocity time graph. We're going to utilize that on our notes here. I'm going to try to sketch out a graph for you here. Let's see if I can drag this guy here at a nice constant velocity. Let's drag him out. Constant velocity. Let's let him just come to a stop for a while. I'm going to pull him backwards and I'm going to speed him up. And then let him slow down, maybe come backwards. Right. Again, both graphs are trying to interpret this guy's here motion, right? We can read it definitely, right? So going forwards here, right, it's trying to be really constant. Again, slope from a position time graph is given, it's the speed. Again, my hands were not super steady here, so you're seeing little minor blips here and there, but you notice the speed is roughly going to be about 1 meter per second going across here, right? We see the parts that when he's at rest, the velocity is 0. When this graph here actually drops to the bottom region here, we know we're going backwards. That means we're going to come back towards the flag here. Whenever we actually start speeding up like that, when there's a curve like that, we saw that the speed actually goes 0, -1, -2, and whatnot. And we're going to see how we're going to actually do this changing of graphs. Let me just give you a quick overview, and then we'll do it on our notes here. Going from position time to velocity time, we knew how to find velocity on a position time. Basically, I need to separate this into multiple segments, and I need to just calculate the slope. So for example, let's pretend here the slope here was a constant 1 meter per second. I would calculate the slant on a position time graph. I would know that the slope means velocity. And I would just say, well, if my slant here is 1 meter per second, and my slant is velocity, and for a velocity time graph here, the velocity is just given by the y-axis, I would just go, well, we were 0 at the beginning. At this time here, I start slanting at 1 meter per second. I'm just going to travel a constant 1 meter per second going across for the entire duration, because I continue traveling at that constant slope for that seconds there. Definitely when there's a change in slope, it's going to be a little bit harder. That's actually going to be like how quickly this one here drops, but we're just going to sort of approximate it. When this line here actually drops downwards, my velocity is going from 0 to -1 to -2. As the magnitude itself gets bigger, I know it's actually speeding up. Depending on how well I actually dragged it would actually differentiate sort of how this curve actually ends up looking. So that's how you take it from position time to velocity time. Going the other way here is a little bit more tedious, but with all the physics that we know, you can do it here. All we're going to do is, because we're interested in finding his displacement, I'm going to try to calculate the area under the curve. In calculus here, you do this as an integral. It's the area that's sort of bounded by this curve here. The area would tell you from this starting point to this ending point here, how much ground does he cover between that time and this time here. And then I just track, well, if his velocity is constant between here, I put a point here, I put a point where he ends up, and constant means constant slope. If the speed actually is changing, if I'm increasing, I do the appropriate curvature to show the speeding up or the slowing down. So have that in the back of your mind here. We're going to just take a quick look at changing graphs. Okay, so back on our OneNote here, let me just sort of give you some ideas with how you're going to change from one graph over to the other graph. Let's start off here. If I want to change, so changing a d versus t, a position time graph, over to a velocity time graph. The thing that we're going to be employing here is we know that on a position time graph, the slope is velocity. So we're going to need to calculate a bunch of velocities here, and then we'll just sketch the corresponding v versus t graph. just like you saw in that simulation here, it's advantageous to put the displacement versus time and the velocity versus time just one over the other. I'm going to remind you again, time is a scalar. When it says here, let's say 2 seconds for displacement time graph, that's the same 2 seconds on velocity time. It's helpful if you just line it up this way, and all we're plotting here is the speed instead of its position. So let me just plot some numbers to this here. Let's say 2, 4, 6, 8 like that. Let's just go 5 and -5 like that. All right. So I could totally start off with him actually beginning at 0. Might be a little more interesting here if I actually start him actually in front of the line to begin with. So let me just ignore that origin point if I can for now. So let's keep this graph here fairly simple. So we have between 0 to 2, he's at 5. And then later on, maybe he climbs up to 10. And maybe this one here starts curving downwards. Right. And then he ends up going into the negatives. Right. So again, sort of what we're going to have to do is we're going to need to calculate the slope at a bunch of these points here. At the beginning, it's not so hard. The slope of this one here is 0. So between 0 and 2 seconds, his speed is 0. Speed is 0 is when it actually intersects this axis here. At 0 seconds, my speed is 0. At 1 second, my speed is 0. At 2 seconds, my speed is 0. So I can just draw this line here. There, I've converted the first segment over pretty easily. Now what about the next part? Well, the next part here, he starts going up at a constant velocity. The slope is constant. So let's calculate what the slope is. So the rise in this case here, I'm going up an extra 5. The time interval is 2. 5 divided by 2 is 2.5. So I'm going to find on my velocity time graph here, I'm going to find where it says 2.5, and I'm going to say at 2 seconds, you start increasing, you start ramping up your slant, so you actually start slanting upwards. So at that point here, you're already 2.5. A little bit later, you're still at that slant. A little bit later, you're still at that slant here, and that slope here is constant. How do we see constant velocity? Is if it stays as a flat line, there is no acceleration. Next part is probably the most interesting here. It's going to be really hard for you to find the slopes at every given point. But let's just talk interpretation here. We know we're going backwards. We know we're actually getting back towards the flag. And we know based on the slant, our slant is starting out fairly narrow and is starting to get more and more and more steep. As it gets more and more steep, that means we're getting faster and faster. How do we show that we're going backwards? Well, on a velocity time graph, I had to have dropped below. We started from maybe having like a 0 slope there, and we gradually get more and more negative. Again, I don't know exactly how quickly this is going to happen, but I'm going to have just a straight line. It's going to end up hitting some more negative slope here. At 3 seconds, at 4 seconds, I was at 0. A little bit later, I'm at -1. A little bit later, I'm -2. A little bit later, I'm -3. My slope is constantly increasing there. And then to the extent here at the end, again, we'll calculate a slope. We're going to drop by 5 over by 2, so that's -2.5. Maybe I drop. This part here actually looks way steeper than what I had earlier. So probably I end up getting sort of way farther down, way steeper, and then only at -2.5 for the last time interval here. So not super exciting for the velocity time graph, because not only are we sort of not allowed to do curves, but we're just sort of, let's find the slope and let's plot it. Well, over that time interval, that's your y value. It's a little bit more interesting going the opposite way, and we'll end off with this. So whatever we're trying to changing, let's change a VT graph, and let's change it to a DT graph. So velocity time versus displacement time. Again, what's sort of inherent in here is when I do a VT graph, I don't know where he is. In fact, I could have given you this graph. I could have realistically started from 0. I could have given you exactly this motion here for the 8 seconds, and you would have done basically a parallel of this. Everything would have been scaled down a little bit here. Your actual position, I still have no clue. All I know is your displacement sort of from 0 to 8 seconds will correspond with what we plot on the graph here. So again, what I'm trying to imply here is I don't actually know where your starting position is, but if you tell me where your starting position is, I can then tell you how your displacement changes over the next 8 seconds. Maybe you were actually behind to start off with, and then you do this curve here. Maybe it then does that shape here from that aspect here. I don't really know where your starting point is, right? I just know if you tell me that over the next 8 seconds, that's where you're going to get. So let's just try one here. For a velocity time graph, again, we're going to use the sort of solution here. On a velocity time graph, the area is the displacement. So there are going to be a bunch of areas that we're going to calculate, and then we need a little bit of interpretation to actually change the rest for us here. So let's imagine changing a VT graph. Again, to make it simple, we're going to line up the time so that whatever time it says on the velocity time graph, that's actually going to match up with the time that it says on the displacement time graph. Let's start off again fairly simple here. Let's go up just in seconds of 1, so 1 second, 2 seconds like that. Let's do, I don't know, 10 meters per second, -10 like this. And let me just draw a shape for you here. Let's go, the graph does this, and then it goes down, and then maybe it does this, and then does this, sure. Alright, so we have a velocity time graph here. Make sure you can interpret through those segments there. But the point of doing this time is trying to do the conversion, trying to convert between one set of graphs to the other graphs. So here's what we're going to do. Again, there is an inherent, we don't know where we are starting. I don't know inherently, am I really at the starting line? Am I starting up here? Am I starting here? That's something that's unknown. So let me just plot it down. Let's pretend we are actually starting at the starting line. That's an assumption. Let's pretend we are actually starting here, although you could totally have this velocity time graph having started any which way, and what you would see is basically your motion from there would just be scaled up or down from there. Relative to the flag, it might be different. So in this case here, let's assume we're at the starting line. What we're going to do is we're going to calculate the area. Well, what's the area of this box here? Well, it's 1 going across, it's 10 going up and down. 1 times 10 gives you an area of positive 10. So by the end of 1 second, you should be 10 meters away. So what I'm going to do is I'm going to plot, let's find where the 10 is. I don't know exactly where. But after 1 second of time, you should be 10 meters away. But that took the entire second for you to cover that entire area. And now what we're going to do in between is we're going to say, well, what happened to the speed in between? In this case here, your speed was a constant 10, a little bit later it's still 10, a little bit later it's still 10. If it's a constant speed, because speed is given by slope, yes, I know I start from here, I know I end up at that point there. I do want to actually have a constant slant in between because the slope is the velocity. So here we're using a constant slope for velocity. No curves or anything like that, okay, because it's constant. Let's do the next segment here. For the next time interval here, let's find the area under the curve. So we're going 1 across, it's 10 going up. It's a triangle, so let's go half base times height. So that area there is a positive 5. So I end up an additional 5 from where I was at 1 second. So 1 second I was at 10. At 2 seconds, I'm actually going to find where it says 15, and I'm going to be here at the end of that triangle. So I know my sort of ending location. And now you need to make an interpretation. Well, what's the speed doing in the segment? So at first I was at 10, a little bit later I'm at 8, a little bit later 6, 4, whatnot. You'll notice that that speed is decreasing. To show that it's decreasing, you have 3 options. Is this going to be a straight line? Is this going to be curved like this, so it's concave down, or is it going to be curved this way? Now the exact curvature will depend on how quickly this happens. I just want you to choose between one of those 3 here. Hopefully you were able to choose to me here. It's actually the one that was concave down, the one that actually curves downwards. You can actually match it up for yourself. Make sure that this graph here is actually saying slow down. Well, let's try it. The slant here at first was really steep. A little bit later is less steep. A little bit later is less steep. My speed is slowing down. That's what's implied here because we know it's slowing down. Let's try the next segment here. Again, we want the area. This time the area bounded by the curve is actually negative. This is a drop by 10. It's also 1 second of time. It's a triangle, so half base times height. So that area is negative 5. So at the end of that second, when I'm at 3 seconds, I actually would be back at 10 meters. And again, you need to interpret it for yourself. Am I speeding up or slowing down? I'm going from a speed of -10, then -9, -6, -4. The negative just tells me backwards. It's the magnitude is actually getting smaller. Now that we're actually sort of bending the other way, again, are we curved concave down? Are we a straight line? Are we curved this way? This one here, because we're actually going backwards, it actually starts curving this way. Again, you can check that for yourself here. The slant at the beginning suddenly was -10. You're going really steep, and then it gets more and more shallow going on. And then we end up at 3:10. At 3 seconds, we're back at 10 meters. And then back to getting a positive velocity, positive velocity, a distance, a time of 1, velocity of 10. 1 times 10 is 10. So I get 10 farther than where I started. I was already at 10, and now I'm going to be at 20. This time it's constant again, so I can use a straight line fit. So a little bit more complicated. I needed to calculate the area, so I know where my ending point is. And then I needed to decide, well, what's the curvature to get me from this point to this point? Mainly for this part here, I want you to be comfortable interpreting a position time graph, a velocity time graph. I'm not going to ask you too much questions with this interpreting or changing of graphs. So make sure you're just good with the interpretation part. If you have any questions, just let me know. Thanks, guys.